not quite. Okay. All right. So everybody take a look up here. I'm hoping you've had enough time to figure out one of them. Again, we'll go in order. I think the first one is the easiest. We've actually looked at that one before. So for 13.6, here is our introduction, okay, to verifying trig identities. So write the word identities here. Now, we're probably going to say this a couple of times today, but an identity is a true equation. So we're going to be verifying that somebody's going to make a statement and they're going to say, hey, this is an equation. We're going to verify and we're going to make sure this is true, okay? So on this one right here, let's see, unit circle, cosine is the adjacent side, that's the x-coordinate. Sine is the opposite, that's the y-coordinate. What can you do with this right triangle right here? Didn't we do this before? No? Anybody? It's a right triangle, right? Somebody want to say what the Pythagorean theorem is? The way I prefer you to say it? Lizzie? Leg squared plus leg squared equals hypotenuse squared. So if I do this one and I do sine squared, because that's one of the legs, plus the other leg squared, so that's going to be cosine squared theta, equals the hypotenuse squared, which is going to be 1 squared, which is just 1. We just verified that sine squared theta plus cosine squared theta is equal to 1. Now, this one, there's a tiny difference on this one, and it's the fact that this is no longer the unit circle, is it?
No.
I mean, I suppose it could be, but it's not the unit circle, okay? So, if we go with leg squared plus leg squared equals hypotenuse squared, I'm going to do leg squared, so I'm going to do opposite squared plus adjacent squared equals hypotenuse squared. Now, that's the Pythagorean theorem applied to that particular right triangle. What on earth would that have to do with trigonometry? Or a better question, how could you turn that into trigonometric ratios? I see some light bulbs going off. I see some people with some ideas. That is not anything to do with trig. But it could be. Zach?
Opposite over hypotenuse equals something.
Okay, so how are we going to get an opposite over hypotenuse? We got some other hands coming up. Hannah, what do you think? Could you divide everything by the what?
Oh yeah, because it goes back.
What is it? Say it again. Hypotenuse. Yes, we could divide everything by the hypotenuse squared. So if I divide by the hypotenuse squared, this is what I'm going to end up with. I'm dividing every term on both sides, so I'm being perfectly fair to everything. So I get a hypotenuse squared over a hypotenuse squared. We've talked about this before. Same thing over same thing is a 1.
Oh my goodness.
Now, both the top and bottom are squared, so couldn't I take this and say opposite over hypotenuse and then square that?
Yeah.
And what is the opposite over the hypotenuse? Psi?
It's sine.
That's the sine of that theta right there. So this is sine squared theta, so wouldn't this turn out to be cosine squared theta? Okay, now, those are the only two that I want to make sure that you understand. Okay? This other one I'm going to show you really quickly.
Hey, Bob.
Hey, McDonald.
How are you today?
Depends on the popcorn situation.
I'm going to have you some popcorn tomorrow.
Okay.
Okay. Will you send Colson Rich to check out, please?
I will.
Thank
We have
you.
some other disappointed customers, but we'll send Colson down.
Can you
Okay.
say Wilson Lab?
Right, right. Okay, so take a look at this. This would be what we call more advanced trigonometry, not introductory trigonometry. This represents any right triangle and a circle on the xy plane. So I'm going to write down y squared plus x squared equals r squared. And then I'm going to recognize that r just represents the hypotenuse. So I'm going to divide both sides by r squared. So this is a different A little bit more coordinate geometry type definition of what the sine is. The sine is y over r. It's the y coordinate over the r coordinate, or over the radius. So this would be x over r, quantity squared, and this is r squared over r squared, so this is a 1. The y coordinate over the radius is another way of saying opposite over hypotenuse, so this is the sine of theta squared, plus the x coordinate over the radius is another way of saying the cosine of theta, so that's the cosine squared of theta, and that equals 1. Now, that definition, that y over r is what sine is, and x over r is what cosine is, that's not introductory trig. That's a little more sophisticated. But what I'm hoping that you can see is a very simple argument that we came up with the other day turns into something like this that's like, oh, okay, I can get that. That turns into something like this where we're not using names and we're not using trig functions to start off with, something we made on the unit circle. We're just saying, hey, this works for any circle of any size, okay? It just so happens that this example right here is either bigger or smaller than this one, and it's convenient when the radius is 1. That's why we like the unit circle so much. The radius is 1, so that means this is y squared. That's the y coordinate squared. The opposite, the sine squared, and so forth. Okay, so here's what we're going to do today. All right, what we're going to do when we verify a trig identity is we are going to prove that it's true. So we're going to use some of the basic trig identities that we have on our little paper that you got to put in that nice sleeve and stuff like that. We're going to use the ones that come from definitions, and we're going to use the reciprocal and quotient identities to verify some trig identities or some equations that are a little bit more complicated. Now, the warm-up is called the fundamental trig identity. We talked about this yesterday. And when we rearrange that, so for example, if we take this and we divide everything by cosine squared, we end up with tangent squared theta plus 1 equals secant squared. And we talked about this the other day. So we've already done this. Remember, tangent goes with secant. If we put cos in front of those, 1 plus cotangent equals cosecant squared. Okay? 1 plus cotangent squared equals cosecant squared. Okay? So what we're basically doing with these true equations is we're moving them around a little bit. So we took the fundamental trig identity, sine squared plus cosine squared equals 1, and we started dividing things, and we came up with tangent squared plus 1 equals secant squared. 1 plus cotangent squared equals cosecant squared. But you can also rearrange these into other things. So I could take this one, the fundamental trig identity, sometimes people call it the Pythagorean identity, and I can say, you know what? What if I just wanted to get cosine squared by itself? Is it a legal algebraic move to subtract the same thing from both sides?
No. Yes.
Apparently in Wilson's world it's not, in everybody else's world it is. Okay? So the cosine squared could also be equal to 1 minus sine squared theta.
Oh, I thought he said illegal.
So that's another way where you could rearrange that. So if anybody showed you and said, hey, cosine squared equals 1 minus sine squared, oh yeah, that's true. I just moved the sine squared to the other side. Could we take this one and solve it for tangent squared? Sure. Subtract 1 from both sides. And we get tangent squared theta equals secant squared theta minus 1. Now, we normally write it like this if we're going to use it, because you could write the minus 1 in front and then plus secant squared. That's a little bit of a hassle. It's kind of nice when we start out an expression with a positive value. And this one's kind of weird. If you wanted to, you could solve this for 1. So you'd do that by subtracting cotangent squared. So if I subtract cotangent squared from both sides, I end up with this. 1 is exactly the same, or in other words, could be replaced with cosecant squared theta minus cotangent squared theta. Now, I mentioned before, we don't use the reciprocal trig functions a whole bunch in this class. We just want to be aware of them. We want to be aware of that. Let me see if I get this right. Secant is related to cosine. Cotangent's easy. It's related to tangent, and cosecant is related to sine. Those are the reciprocal ones. Those are how they're related. So here's what we're going to be doing, and I think you're going to like the assignment. It says, take the result in example 1a above, which is this, and factor the binomial. So we're going to take this and we're going to break it into more pieces. So I heard somebody say, I won't say their name, but it was Dane. Okay, what's a binomial? Can somebody raise their hand and tell us what a binomial is?
I don't even know either name.
Raise your hand if you don't know what a binomial is. Okay, put your hands down. Raise your hand if you know what a bicycle is.
Oh,
Sweet. How many wheels does a bike have? Two.
Unless it's just
So we're going to... Thanks. Thanks for changing the question. Okay? So if you take a look at this right here, this has two terms. That is the binomial side. This has one term. That's a monomial. This has two terms. That's a binomial. So we're going to take the binomial and we're going to factor this. Now, we are stretching back and thinking back to, holy cow, we did factoring like 7 units ago. But we have had some factors of the day. I want you to take a look at that.
Well, frick.
There's a name for it. Do you know what it is? So here's the problem with taking the square root of both sides. First of all, yeah, you could take the square root, but you can't just take the square root of 2 pieces. We'd be stuck with that ugliness underneath the radical. You couldn't take the square root of 1. Okay? Good try.
Difference of squares.
Ooh, very good. Would you say that nice and loud, Jack?
Difference of squares.
This is a perfect square of 1, and this is a perfect square of sine theta. So this factors to 1 minus sine theta and 1 plus sine theta. Okay? So what we're doing here is we're just getting used to the fact, and again, I've said this before, this is what people struggle with when they get to calculus. That's some funky algebra. That is not trigonometry. That's algebra. We're rearranging this using algebra, and that's what we do when we verify trigonometry or trigonometric identities, is we use some algebra to verify that some equation is true. We're using our algebra skills, not really our trigonometry skills. Okay? So when you look at something like this and say, holy cow, how did they go from here to here? So I need everybody looking up here. This will happen in some future class. You'll see something like this and go, okay, I remember how we did this up above. We just moved the sine squared to the other side. But I have no freaking idea what happened here. Difference of squares is where you would get lost. And that's why all of those factoring skills and all those basic equation solving skills, and when you start learning about logarithms and exponentials and all sorts of stuff, those are the skills that you're going to be depending on when you take calculus. Okay? So all I did here was use a factoring technique that we've been working on for quite a while. All right? So slide down here and I'm going to show you what we're going to do. We're going to do some fairly simple examples today. We're going to be verifying an identity. That right there is an identity. So somebody is claiming that this equation is true. What we want to do is we want to make sure that it's true. So to verify an identity, we need to show that the two sides of the equation are indeed equal to each other. Generally speaking, there is no perfect way to do this, but generally speaking, it's better to work on just one side of the equation. Okay, it's a little standard to just work on one side and make it look like the other side. Start with the side that looks more complicated. The reason we want to work on the side that's more complicated is we have been taught for years to simplify things, and we're pretty good at that. We're not very good at making things look more complex. As an example of that, right up here, this looks great. This looks more complicated. Okay, we're not very good at going this way. We're pretty good at going the other way. So we want to work on the complicated side and make it look more simple. Okay, use the basic identities that we've learned. Sometimes writing everything in terms of, I'm going to write sine and cosine. Sometimes that's going to be a good way to go. In fact, I would say more often than not, if you write everything in terms of sines and cosines, that's going to be really helpful. And then would you write in big capital letters? You're going to be using your algebra skills a whole bunch. So, factoring, combining fractions, breaking fractions up, squaring binomials, multiplying by the conjugate, substitution, simplifying complex fractions and stuff like that. All very useful. Now, you may get frustrated. Try and keep at it. The ones we're giving you on the assignment, and there's only 10 of them, some of them are really, really quick. Okay? Yep.
Some are hard.
So before I start anything, there is often more than one way to do it. So just because your friend did it one way, as long as they legally and algebraically did it, totally fine. Okay, so we want to make sure that this is actually true. The more complicated side is this one. If you ever see a trig function squared, most of the time you're going to be using a Pythagorean identity. So I want to come back up here, and we've got a secant squared and we've got a tangent squared. So we're going to come right here. Hey, wait a second. Tangent squared is secant squared minus 1. And secant squared is tangent squared plus 1. So I'm going to highlight the two of these. And this is where it comes in and whether or not somebody's going to do it one way or do it another way. Now, most of us would be using this one right here, so I want to show you something. Secant squared is exactly the same as this, right? So, where there used to be a secant squared, what I'm going to do is I'm going to replace that. I'm going to replace a secant squared with a tangent squared theta plus 1 minus a tangent squared theta. That was in the original problem. Isn't it true that secant squared theta is the same as tangent squared plus 1?
Yes.
Now, I think I say this later on, but you'll notice that I'm saying tangent squared and secant squared, and I'm not saying theta. There are people that will actually drop the thetas and the x's and stuff like that, and they'll just write tangent squared, secant squared, and stuff like that. I'm okay with that on work. I would prefer that not happen on a test, and you definitely can't write the answer that way. So I'm going to do it in the proper way, if that's okay. Everybody good? Okay. Do I need that set of parentheses? No. So this is tangent squared theta plus 1 minus tangent squared theta. And isn't this tangent squared theta minus tangent squared theta? Isn't that same thing minus same thing? So this side says 1 and the other side says 1. Did we get it?
Yeah.
We did. Okay? Now, I'm going to slide down here and I want to show you something else. You do not have to write this down, I just want you to watch. Don't write this down, just watch. So this is 1 equals, what I'm going to do is I'm going to use this one. I'm going to replace tangent squared theta with secant squared minus 1. So this is secant squared theta minus, if I'm going to do a minus, I better plug it in parentheses. People make mistakes with this all the time. If I'm going to subtract more than one thing, I got to make sure I subtract everything that I'm subtracting. So I'm going to write in secant squared theta minus 1. So this is secant squared theta minus secant squared theta minus minus 1 is a plus 1. Do those cancel out?
Yeah.
Yes, they do. Does 1 equal 1? There we go. Verified. Got it? Okay. That actually, I think it's one of the tougher ones. Okay? There's more than one way to do it. You'll notice on this one, we're now writing things in terms of x. Does it matter what variable we use for an angle?
No.
Nope. Doesn't make any difference at all. So we could use theta, we could use alpha, beta, gamma. Those are the Greek letters that are often used. We can use x, we can use y. Whatever you want to use is totally okay. So I want you to take a look at this right here. Which side's more complicated?
The left.
I think the left side's more complicated. Does anybody notice anything that the two of those have in common? They have a cosine.
X.
Okay, so hold on just a second. They do not have an x.
The x is the angle.
X is the angle. Cosine doesn't mean anything without the x. The x in this case doesn't mean anything without the trig function. So those are stuck together. They both have a cosine of x. So if they both have a cosine of x, what if I factor out the cosine of x? What would be left of cosine of x if I take out a cosine of x? 1. What's left of a minus cosine x sine squared x? Minus sine squared x. Now, would you do me a favor? And would you look at the other side? And you will find there is a 1 minus sine squared somewhere on there. Look at the other side for a second.
Is equal to cosine squared. But it's cubed, not squared, so.
Okay. Watch. Okay, no, thanks. Okay, see the red stuff up there? That's the thinking. Now, I'm okay with you thinking and just writing sine squared plus cosine squared equals 1. If I move the sine squared to the other side, wherever I say a 1 minus sine squared, Zach, what can I put wherever there's a 1 minus sine squared since these two things are equal? I can put a cosine squared. So what I'm going to do is I'm going to put in right here, I'm going to put a cosine squared x. And out front here is a cosine of x. So if I have a cosine of x times a cosine squared of x, I have, whoops, cosine cubed x. And does it equal the other side? Yes, it does. Good? Okay. Is there a lot of work here?
Yeah. No.
Is there a lot of thinking?
Yes.
Yeah, and a lot of algebra. Okay, I want you to take a look at this one. Implied multiplication here. Sine x times tangent x plus cosine of x equals secant x. Oh, well, you've got your paper. That's what your paper's for. Take a look at that sheet. This is one of those where writing everything in terms of sines and cosines is good. Now I'm going to put Crew on the spot because he says he doesn't know. Crew, what's another way to write tangent?
Is it just sine over cosine?
Sine over cosine. It is.
I don't know.
Plus cosine of x. Now we're going to leave the secant alone for right now. We're working on the more complicated side. So this is, take a good look at this, sine x times sine x, sine squared x over cosine x plus cosine x. Little bit of trig to change the tangent into sine over cosine. Algebra to multiply the two of those together and get it squared. Algebra and arithmetic coming up next. Now I'm going to give somebody a hint. I'm seeing some eyes that are going, ooh, I think I might know. We're good at simplifying things. We're good at simplifying things. We're good at putting them together. We're good at combining things. Anybody got an idea? Yeah. Okay, not quite cross multiply, but we can add it. How do you add fractions? Nope, that's for proportions. Zach.
Is it where you, for the cosine over 1, you would times both sides by cosine?
You would times the top and bottom by the same thing. You've been doing this since elementary school. You're getting a common denominator. So I'm going to multiply the bottom by cosine of x, and I'm going to multiply the top by cosine of x. So now what I have is this. I have the sine squared of x over cosine, and then I have plus, I have cosine squared of x over cosine, and now I can combine those together. So what I have is sine squared x plus cosine squared x over cosine, and I have one tiny thing left to do. Hold on. Remember what I said. If you ever see a trig function squared, you are probably going to use a Pythagorean identity. What's sine squared plus cosine squared? 1. So what's the top? What's the top? 1. What's the bottom? Cosine of x. Isn't that exactly the same thing as secant of x?
I guess so.
Did we verify it? Yes, we did. Those two sides are equal.
How am I supposed to figure that out myself?
You're supposed to practice. Okay, any questions there? Okay, got a couple more to look at. You'll notice, this is what I say down below. There are some people that do things like this. We'll look at a couple more problems. They get a little sloppy. They're not writing the angles. I'm okay with that when you're talking about it, okay, not when you're showing the work, okay? They really don't mean anything without plugging those in, okay? We'll say tangent is sine over cosine to shorten things a bit. We know what you mean, okay? So it's fine to talk that way, but you want to write things precisely, okay? Would you put a star by this one right here? We talked about this earlier, but I just want to make sure you're clear with this. When we write a trig function, you have to write an angle that we're plugging into the trig function. Fun little fact, what we plug into a function is called an argument, okay? So if you were to write cosine and not put anything there to plug into it, it's kind of like writing a square root and not putting anything underneath it. So this doesn't mean anything until you plug an angle into it, just like this doesn't mean anything into it, or doesn't mean anything unless you plug a number into it so it can find the square root. Everybody good there? Okay, so keep those things in mind. Let's take a look at this one right here. Which side looks more complicated? What do you think?
Right.
You think right side? Okay, I think left side.
Oh,
I did left side.
The reason I think left side is we are better at putting things together than we are at breaking them apart. So you would have to take one term and break it into two. We're not very good at that. We're much better at taking two terms and combining them into one. So I'm going to ask somebody, I don't know, it might be Crew. Crew, what's the tangent?
What? Oh,
What's the tangent?
sine x over cosine.
Thank you very much. Okay, Jack, what's the cotangent?
I don't know. Let me see.
Come on, Jack, log in.
It's
One
opposite.
It's the
over
reciprocal.
1 over tangent.
You could do that, but we're writing it in terms of sine and cosine, so it's just the reciprocal of this.
Oh, yeah.
You have to do it that way.
No, you don't have to, but I.
You just make it 1 over
Wait.
tan, and then treat that one as tan, and then get tan squared.
You could try that.
That's what I was thinking.
You could try that, but remember, hold on.
Like,
Hold on. Remember, there's more than one way to do this, and what's going to often happen when you start doing these is you're going to bark up the wrong tree for a while, and then you have to go back and start over. So I think you would be barking up the wrong tree. I'm not saying you can't do it that way. I'm saying you would probably be barking up the wrong tree. So take a look at this. Everything's in terms of sines and cosines. I want to put these together. What does this one need? To common denominator. What does this one need? What does the first one need?
sine.
It needs a sine. So I'm going to multiply the bottom by sine. So I have to multiply the top by sine. Lydia, what does this one need? If I'm going to get a common denominator. Very good. We need a cosine of x here and we need a cosine of x here. So here's what I've got. On the bottom, I have this. I have a sine of x and a cosine of x. On the top I have, when I combine these together, this is a sine squared of x plus a cosine squared of x. We're pretty good at putting things together, right? D, what's the top?
Top one.
Yep.
Um,
Sine squared plus cosine squared.
that equals tan. No.
Gotta know this. The fundamental trig identity. Sine squared plus cosine squared equals 1. So I have a 1 on the top, and I have a sine of x and a cosine of x here. Now, remember, we got to use all of our algebra skills here, so take a look at this. Can I take this and say, well, that's the same as 1 over the sine of x and 1 over the cosine of x just multiplied together? Is it okay to take a fraction and break it apart like that? Absolutely. What's 1 over sine? Cosecant. What's 1 over cosine? Secant. Okay, is that, I have to shrink this down just a little bit. Is that the same thing as the other side? Yeah, all you have, it's commutative property of multiplication. Secant of x times the cosecant of x. Same thing as we had right here, so that's verified. Any questions?
Well, my way it's weird.
Did it work?
I got stuck on secant squared x plus 1.
Oh no, you
Or
got
minus
stuck. You got stuck. Okay, all right. Take a look at this one. This one has a star by it. This is more difficult than anything I would ask you to do. So, I want you to look at that. We've done stuff like it. You look at it. I'm going to pass out the assignment, and I'm going to I'll give you a hint on this next one. Will you give that one to Crew?
Is the hint I'm doing it wrong already?
The hint is on this one.
Oh wait, I can't do it that way.
I need a lot.
Bonus. Multiple from 2.
What's our hint? Just give us how we started. That's our hint.
Okay. Your hint is we're going to work on this side. It's more complicated, right? The left side?
Yeah,
I believe
already.
so.
If we're going to combine these together, what do we need?
Common denominator.
A common denominator. So I'm going to put parentheses on this one. What denominator does this need?
Cosine x.
Cosine of x. What denominator does this one need? What other thing do we need? 1 plus
But is
sine of
that-
x. Nope. Okay. So I have to multiply the top and bottom by 1 plus sine of x. Now, watch. This side's pretty easy because it's just cosine times cosine, right? So this is going to be cosine squared of, cosine squared of x. This is a binomial. That's a binomial. So the bottom is going to be cosine x, 1 plus sine of x. Okay. See what you can do with that.
What just happened?
You'll have to try some stuff, see what you can do with that. You might bark up the wrong tree for a while, you might get frustrated, but give that a shot. Now, I'm going to go ahead and stop this, and I'm going to show you on the, well, no, I'll go ahead and do number 1. Okay?
Can we get skips on this one, please?
Skips, are you serious?
Yes. Let's skip 2 and 2.
No, I want you to try, but I will give you some help tomorrow before we correct. Si, do we have anything new tomorrow? No. Caleb, what do you think? More complicated side here, right? What do you think we ought to do?
Maybe you should simplify the tangent.
Right, what do you want to write tangent as?
Sine of theta over cosine.
I love the fact that he's saying it the right way. Angela, what can we do? You see what we can do with cosine on the top and cosine on the bottom? We can just cancel them, right? Cross cancel here. Does sine of theta equal sine of theta? Done, verified. Okay. There's number 1. You have several problems that are relatively easy. They'll get progressively more difficult. Okay, give those a shot.